Good afternoon from All Children's again to everyone for Shine 2023. I would like to invite up our last guest lecturer for this afternoon, Dr. Ernest Amanqua, who is one of our wonderful biostatisticians here at All Children's Hospital, and personally has been a wonderful partner to me and many of my other nursing colleagues in many projects here over the last many years that he's been with All Children's. And I'm really excited today to have him present for us Statistics 101 for the bedside nurse. I think it's something that all of us should have a little bit knowledge of, and it's usually a pretty scary topic. So hopefully he's going to demyth this for us. So welcome, Ernest.
Thank you, Christina, for that introduction. So Christina is one of my friends here at All Children's. Even though she doesn't see me as a friend, she is one of my friends here. We've been working together for a long time since I've been here, and I really appreciate her collaboration. Yeah. All right, so this is my disclaimer here, my disclosure. I serve on the Safety and Data Monitoring Board for two pharma companies, Pfizer and Bristol Myers Squibb. So yeah, usually, we will do a study, we collect the data, and then we look at the data rows and columns on Excel spreadsheet or whatever we use to collect our data, and we are kind of shaking our head and this doesn't make any sense. So we say, maybe statistics can help. So what I would like to do is, most of the time we think that you consult the statistician after you've collected your data and you need help with the analysis. But statisticians get involved earlier than that. So what I will do is I will go through the framework of a study, right? Usually how we conceptualize a study, and tell you a bit of the stuff that you need to do before you actually get to the point where you collect your data. So I'll also talk about sample size, which is very critical when you are planning a study. And then we will get to the statistical analysis that most clinicians think statisticians do, but we do a lot more. So we can help you with your research question. Even when you have an idea, we can help you formulate that idea into a research question. So usually this is the framework for a study. So when you are trying to do a study, you have a population that you want to study, and you want to make statements after your study. You find your results and you want to make statements about that population. So your population will be the individuals that you would like to generalize your study to. Unfortunately, you cannot study everyone in the population because the population can be large. For example, if you want to do a study and make statements about the population in the US, let's say you want to know the incidence of VTE in the US adult population, right? You can go to the different hospitals because this is something that occurs in the hospital. But imagine something that does not occur in the hospital, but in the population. You can't go into every home and ask people if you have the condition or not across the US. So what we usually do is you take a sample out of the population, and hopefully the sample will be representative of your population so that you can make statements about the population. So your sample is just the subset of the population that you select to do your study on. And most of the time you have two arms of your study, whether it's a trial that you are doing, you give the drug to one group and you give a placebo to the other group, or if it's even a prospective or observational study, you have a group that have a certain exposure that you would like to study, and then you want to compare them to another group that does not have the exposure that you are interested in as your control, so that you can compare the two. So when I say treatment and control, that is what I mean. So you will look at your outcome in the treatment group and you will look at your outcome in the control group, and then you make comparison, right? So let's say you want to look at VTE is what I've been working on since I've been here, so I'll be using that as an example throughout. But my area of research is cancer, but I've been doing a lot of VTE work here. So I might be moving around cancer and VTE. So VTE, I'm sure we have nurses in the room, so everybody knows venous thromboembolism. So you look at your outcome. Let's say you want to see if CVC given lines increases the risk of VTE. So you have a population that got a line, like it could be a PICC line or any line in the hospital, and then you have patients that did not receive a line. And then you look at the incidence of VTE in those that have a line and those that do not have a line. And then you can compare them, right? And then make statements whether lines increase your risk for VTE. So you can make statements about the sample that you chose to study. But ultimately, you want to make statements about the population, right? So to do that, we use statistical methods. That is where the statistical inference comes in. It allows you to move your results from your subset sample to your population. So when you are performing a t-test or when you are performing a chi-square test, that is what you are trying to do, to make inference about your population. Okay, so moving on to the next thing that we usually do after establishing, the framework of the study, you talk with your statistician and then you decide the population you want to study, you get your sample, and then you want to know how many people do I study. So that is what we term sample size. So it's a rough estimate, a guesstimate of the number of people that you will need in your study to be able to draw conclusions. So that is your sample size. And it's an ethical issue. Sometimes when I tell people that sample size is an ethical issue, they are like, what are you talking about? It is, because if you have very small number of people in your study, right, you will not be able to draw any conclusions, and you've wasted the time of patients and whatever you expose them to, so it will not be ethical. And if you expose patients, a large number of patients to whatever you are studying, maybe you need a fewer number, but you included a large sample size and you expose so many people to what you are trying to study. That is also unethical. So you want to be able to determine, the appropriate number that you will need for your study. And remember, it's an estimate. So I have here that, a small sample size might fail to answer your research question, and an extremely large sample size will make you expose so many people to what you want to study unnecessarily. So after you've done that, this is the crux of what we do, right? You want to test a hypothesis, or you want to calculate your sample size, right? So these are the ingredients that you need to determine your sample size. So for example, if you want to speak with a statistician, this whole idea is not to make you statisticians, but to give you enough information so that you can have conversations with statisticians and have an idea of the process, right? So if you are going to your statistician, the statistician might ask you, what hypothesis are you trying to test, right? Maybe you say, oh, I would like to know if the mean weight of certain group of children is higher than the mean weight of another group. So that is the hypothesis you are trying to test. And then we also need the power of the study. That is the ability to detect a difference between groups if there is actually a difference. And we usually set it at 80%, right? So think of power like a light bulb, right? I usually use microscope, but I think a light bulb might also work. So maybe you have a big dark room like we have here, right? And if you light a small bulb and you are trying to look at to distinguish the people who are sitting in the back, you might be able to see that there are people there, but you might not know whether this is Jade or this is a different person, right? Because you don't have enough power. Your bulb does not shine bright enough for you to do that. And it's the same with steady power. You might not have sufficient power if you have a small sample size to be able to detect differences. That is why we always say that it's important to power your study adequately. And then you also set what we call the alpha level or liberally as the statistical significant level. So we usually set that at 5%. Or so most of the time you hear that if P is less than 0.05, then we are saying that what we found is statistically significant. So that is where that comes from. And then you also need your effect size. So if you are comparing two groups, your statistician might ask you, what kind of difference do you anticipate to see? And you are like, yeah, that's why I'm doing the study. If I knew the difference, I wouldn't be doing the study. Yeah, you're right. Yes. But we always want an idea, right? So you can get that from previous studies. So maybe someone has done what you are trying to do, but they did it on a smaller scale. Or maybe you did it yourself on a small sample, but you want to do a larger study. And so we will be interested in the difference that you saw in your pilot study or preliminary study. Or sometimes nobody has ever done anything on the topic and it's very new. So you are like, I don't know, but we will touch on that later. You have to come up with a difference to be able to determine your sample size. So this is where you can get those effect sizes from previous studies. And it has to be clinically meaningful, right? Because let's say if you want to look at the effect of a drug, right? Compare two drugs, a newer drug and an older drug. And if you want to see the difference in outcomes, you want to know if this difference that I see will cause a change in practice, right? Because you might be able to see a tiny difference, which might be statistically significant, but it might not be clinically important. Let's say you come up with you are testing a new hypertension medication, and then you compare it to what we already have as usual care, and you see a difference of, let's say, 0.1 in systolic pressure. Will that cause you to change practice, even though it's statistically significant, right? So you want to set your effect size at something that maybe if I see a difference of 10 in systolic and a difference of 15 in diastolic, I'm just throwing out numbers, forgive, that will cause practice change. That means the drug is good. So that is where you want to be at to be able to do your sample size calculation. But sometimes you don't have any clue. There's nothing out there and you don't have any idea what the clinically meaningful difference should be. So in that case, we have generic stuff that we can use. So we can say that, okay, we want to detect a small effect size, or we want to detect a medium effect size or a large effect size. And we can use that to do the sample size estimation for the study. But we don't usually want to be there. We want to work with actual sizes. So here I'm showing a relationship between sample size and power of the study, right? So as I mentioned earlier, as you increase your sample size, the power of the study also increases. So usually you want to be here at 80% or 0.8, right? So for this study, we are trying to look at a difference or effect size of 0.9. We have set our alpha level at 0.05. So if we look at a power of 80%, we will need about 38 participants to be able to see that effect size. But if we want more power, like 90%, then we will need about 50 participants to do that. So that is the relationship between sample size and power. And this is another way of looking at it, but this is your effect size and your total sample size, right? So just figure out what I said earlier. If you have a large sample size, you'll be able to see tiny differences, right? But if your sample size is small, the difference has to be very large to be able to detect it. So as you are planning your study, you have to think about those things that, okay, I want to see a tiny effect size. So I need a large sample size. Will I have enough patients here in the hospital to be able to do that study? So those are the things you think about as you plan your study. And this is additional information that you can give to your statistician, right? Your predictor or your outcome variable and how they will be measured. So if you are trying to study, let's say, the effect of anticoagulant on VTE prevention, right? So your statistician might ask you, what are you trying to study? And you say, oh yeah, I want to see whether they develop VTE or not when they are given, prophy anticoagulation. And then you say, oh, okay, so your outcome is the VTE, right? And your predictor, what you are trying to study and thinking that it might cause or lead to a change in something, that is what we call your predictor. That is your anticoagulant, and your outcome is the VTE. And then the statistician will also like to know the number of groups that you are studying. So if you have 2 groups, or if you want to do a cluster sample size study, right? And by clustering, if you want to study, the behavior of nurses, right, across different hospitals. Nurses are within a hospital, and in statistics terms, we think that nurses within a hospital might be similar than nurses in a different hospital. So we say that nurses in a hospital are clustered because they are somehow related. So we want to take that into consideration when we are planning a study. And of course, you also need the effect size. And when we talk about variables, you hear that often. So we hear, okay, what variables are you trying to collect data on? So your variables are usually, what you are using to quantify the phenomenon that you are trying to study. So if you want to do like a study on adiposity and let's say cancer risk, you want to know how are you going to measure adiposity, right? So your variable might be body mass index. Yeah, that is what I'm using to measure adiposity, or maybe waist circumference. Whatever you use, that will be your variable, because that is what you are trying to use to capture the phenomenon that you want to study. So anytime we talk about variables, that is what we mean. And statisticians can help you to actually pick the variables that are valid to answer your research question, right? For example, if you are interested in visceral fat, we all know that BMI has issues, right? So maybe the statistician will propose that, can we probably use waist circumference or waist to hip ratio, or maybe have one of those devices that will actually measure your lean body mass and all that stuff. So you want variables that can actually help you to answer your question. And there are different types of variables. We have the main 2 types that we talk about are categorical variables and numerical variables. So under categorical variables, we have what we call the dichotomous variable, when you have only 2 levels. So think about a situation if you want to study cancer, right? You group people into those that have cancer and those that do not have cancer. So your variable is only 2 levels. So that will be a dichotomous variable. And you can have a nominal variable that can be more than 2 levels, right? For example, blood group. You have a AB, and O, right? So those are different categories. But the difference between nominal and ordinal that I will talk about next is that, we know that A is different from B, and there's no order to them. A is not better than B. It's just random, right? It's just like maybe race or ethnicity. We know that it's randomly distributed. One is not better than the other. So we have grouped them as nominal. So you can have blood group A, you can have blood group B, or you can have black, you can have white, you can have Asian, you can have that. So different groups. But with ordinal, right, you can have those groups. And an example is the Likert scale that some of you might have used in your studies, right? Whereby you can have like poor, average, good, very good, and excellent. So there's a kind of order to them. You know that, good is better than average, but we don't know whether the difference between poor and average is the same as the difference between average and good. Even though there's an order to them, the difference between them, we don't know if they are equal or not. All we know is one is better than the other. So that will be your ordinal variable. And then we have the numerical variable. And with that, there are 2 main ones. We have your continuous variable, that is infinity. You can have decimal points, fractions in them. For example, weight. Someone can be 70.1 kilos, right? So you can have decimal fractions. That will be your continuous variable. And then we have the discrete variables, continuous variable. And with that, it's whole numbers, right? So let's say you want to count someone's extended family members. It can be 9 or 10 or 11. The fact that someone doesn't like their uncle doesn't mean that person can be half. And you say, oh yeah, my extended family members are 4.5 because I don't like my uncle. You can't do that, right? So some of the things come in whole numbers, and those are your discrete continuous variables. And in statistics, whenever you are doing a study, if you can use a continuous variable, we prefer that to categorical because you gain more power when you use continuous variables. And so after you know your variables and have collected your data, it will be very nice if you can just put all the data in the computer and say, I want to compare the two groups, and then it will do everything for you. Unfortunately, we are not there yet. So we have to actually do the analysis, and you will need the help of a statistician, or you can train yourself to be able to do that. But we always encourage you to partner with a statistician so that you can do a rigorous study, right? You can do it yourself, that is fine, but sometimes statisticians can view things in a way that you don't view it that way. And it's just because of the differences in training. So it's always a good thing to partner with them. So usually after you collect your data, what you want to do is you want to display them graphically or in a tabular form so that you can get to know your data, right? You can know what is going on. So on the left, you see that I have a table there showing the age groups of a study, right? So I know that there are 5 people in the 0.0 to 5 year age group. I know you can also present it as a pie chart, right? Which is graphical and it shows you, the distribution in different colors, or you can use a bar graph to the far right. That will show you the distribution too. So it helps you to see what is going on in your data. And we always encourage you to do this because you will be able to detect errors by visually looking at your data. And we know that each of these have their own limitations. So depending on what you are trying to say, you might pick one over the other. And with continuous variables, you can also choose different ways to visualize them. So on the top left corner is a histogram that you can use. And then, you looking at this, it will tell you if the distribution is normal, because if it's normal, you can use a mean. If it's not normal, you don't want to use a mean to represent the data, right? So it's always good to look at your data. And I've mentioned this, that depending on what you want to communicate, you will use different visuals. So now you get to the inferential part where you want to make a connection between, your study results in your sample. You want to make a connection to the population that you want to study. And so we have 2 main areas that we use to do inference in statistics. And we have the hypothesis testing, and then we have the estimation. So hypothesis testing is, you are trying to make a decision. You look at your results and you want to make a decision. So you want to evaluate the evidence and make a claim. But you want to put limits around your claim to say that the chances of, me making an error on this claim will be this, right? Somehow, so you want to provide an idea to people that, there is an error in the claim that you are making, right? So this framework is very good because it's very objective, so that when I do a study here and I apply that framework, I will end up with the same, conclusion if somebody should repeat the study in Australia, or if somebody should repeat the study in Ghana, right? We'll come up with the same results or conclusions. So it helps, but it has been abused over the years. But this is a good framework, objective framework. When it's used well, it helps to make a decision. So this is the framework. You specify your hypothesis, just like determining your sample size, right? and you specify your significance level, which is usually the 0.05 I mentioned earlier on. And then you calculate your test statistics, depending on what you are trying to study. If you are studying means, you do a t-test. If you are studying proportions, you do a chi-square test, right? And then you make a decision rule and say that if my p-value that I get from my study is less than 0.05, then I will reject my null hypothesis, right? But if it's higher than that, then I'll fail to reject it. So that is the framework that you use. And here I'm showing the different types of tests that you can do depending on your study question. So I'll quickly go through an example. I know we have about 3 more minutes. So I'll quickly go through an example, because if you are like me, you'll say that, yeah, I like to hear you talk, but I'm a do person. I always like to see an example, right? So this is an example whereby we are trying to compare the weight between 2 groups, right? So what we did first is we want to look at the distribution of the 2 groups. And if you look at this here, this is one of the groups, and on your right is the second group. So when you look at the distribution, you see that it's not normally distributed. There's a tail here, right? And when it's not normally distributed, you don't want to use normal test to compare the groups. But in this case, I intentionally use the normal test to point out a point to you, right? And this line below them also tells you if your data is normal, it will fall on this straight line here. But you see that it deviates from that straight line. So it means it's not normally distributed. But still, we went ahead. So if you did not visualize your data and you just run your test, this is what you will get. You see that the difference for the 2 groups is 1.4, and your p-value is less than 0.001, meaning that it's statistically significant. The difference is statistically significant, right? So we will say that, oh yeah, we made a major discovery. We found that there's a difference between the 2 groups and it's statistically significant. And then the statistician will look at it and say, wait a minute, let's go back to your distribution, right? We see that they are not normally distributed. So you are not supposed to be using a t-test to compare them. But this is what we see in the literature all the time. People do not visualize their data, so they don't use the appropriate test. And then they draw conclusions. So when you see people drawing conclusions like this, try to question what test did they use? Did they fit the assumptions, right? And if it didn't, then you have to question the results, even though it's significant and it's exciting. So I will just stop here because of time, right? Because of the abuse, right? There have been people pushing for the retirement of statistical significance, because you can see a statistical significant difference everywhere, people reporting, and even if people don't see a statistical significant difference, they don't want to report their findings. So it has been abused. And in the past few years, there's been a push to retire it, but it's a very good thing to do. It just has to be used appropriately. All right, so I will stop here and I'll be willing to take any questions. So this is my summary slide here. And the last point is that, to consult a statistician after you do your experiment will be like asking the person to do a post-mortem. They can probably tell you why your study did not work, but they cannot go back to fix it. Okay, these are my references. Thank you very much.
Thank you very much. Do we have any questions here in the room? I think we probably could talk about 3 hours about retirement of statistical significance. I think that's probably a whole nother lecture in and of itself.
I agree.
Certainly, I think you're right about the abuse of that. But does anyone have any questions here? We didn't have any online, so I just wanted to ask. Let me double check just to make sure we don't miss something. If they're sending me. No questions, just some positive feedback. All righty. Well, thank you so very much. We really appreciate you being here and sharing your information. And as always, the presentations will be converted over into virtual sessions that you can go back and even re-listen to them and catch up on the ones that will be here live. So thanks everybody for attending. We appreciate it. Have a great afternoon. Thank you, Ernest.